All right, welcome to Office Hours Before Test 2. We're going to be talking about all sorts of nucleophile, electrophile, E1, E2, SN1, SN2. I'm sure of it. So thank you guys for joining me. Those of you guys who took the time to come to this office hours, seems to be a fair amount of you guys. Yeah, so let's get started. Do you guys have anything in particular you want to start with, or should I just start doing problems?
With me, I was like mainly not even like confused, just like what we did was like a little harder today.
Okay, so let's give just a short description. I think I didn't do a great job of giving an overall. I don't know how to move this thing. There we go. Just an overall sense of what we're doing. So today was about the last little percent. The If you understand everything else, these are the make or breaks. This is what's going to get you 100. This is the ticky tack stuff. This is stuff I care a little bit less about. This is not the main idea. These are alternate ideas. All right. So the first one would be, you know, let's say I have that and I'm doing some form of
You.
how's it going? All right. Let's say we have that. I'm trying to make it very clear. OTS that looks weird, but we talked about that. That is equivalent to a halogen. That's an oxygen equivalent of a halogen. You might see something like that on the test. TS is just a large group that we put on oxygen to make it a good leaving group. That's all it is. All right. So I see a halogen, I see a leaving group. My first thought is, well, I've got to decide if this is going to be E1, E2, SN1, SN2. All right. How do I do that? Well, the first thought is I see a metal. That's where my eyes should always go. You see a metal, that's a red flag. I'm going to draw it out. All right. So I know it's either an SN2 or an E2 because I have something that's charged present. Done. Heat tells me that I'm probably going to be using an E2 instead of an SN2. All right. So when I do an E2 on this thing, I have to look at the leaving group, the carbon with the leaving group, and I have to look at one carbon away. Right. That's where the protons I could potentially take are. So elimination, I'm always taking a proton. We call it a beta proton because it is. That's the alpha proton, the one with the leaving group. This is the beta proton. So I'm going to be taking one of those protons. The question is which one? So if you've got this far, you knew that we're E2 because of all the various factors I talked about. You're doing great. You're doing wonderful. But this is the not partial credit. This is the full credit. Which one of these protons do I take? Well, a guy named Zaitsev found that they always tended to form this elimination product. So this would be my major product, whereas taking the other one would get me this double bond. That would be my minor product. You see way more of this than the other one. And it has to do with this double bond and the product being unstable and having one, two things coming off of it, as opposed to this double bond, which only has one thing coming off of it. We call this a disubstituted and a monosubstituted double bond because how many things are coming off of the double bond? All right. So this is Zaitsev rule.
On the exam, do you want us to draw the major and minor product each time, or just the major?
Either draw them both or just the major. I'm cool with either.
Okay, thank you.
The only exception to Zaitsev's rule is if I had a super bulky base. If I had something that looks like this. So this is charged. Therefore, I'm looking at either some kind of two. It's very bulky. So that means that I'm going to get an E2, right? Bulky bases do E2s. This big guy would have trouble getting into that carbon. So in this case, he takes this hydrogen. He forms, this would be the major product. If I give you this question, I'm going to make it very obvious. Essentially, I'm going to give you sodium or potassium terpetoxide. I'm going to expect that you know that, hey, this is a bulky base. It's not going to form the Hoffman product. Or sorry, it's not going to form the Zysev's product. It's going to form the Hoffman product. I don't care that you know the name. It's going to form the less stable one because, again, this guy is so big that he wants to interact with the less substituted carbon. He's going to take the path of least resistance. This is kind of a rare question. It's more that this is going to be just kind of seamlessly integrated into stuff. Like if I look at this practice test, like here, right off, this is an elimination. Which hydrogen do I take? Well, I'm going to take the more substituted one. Like it's kind of already built into questions that you were already doing, if that makes sense. Like you had to choose one of the two of them anyways. So I'm just saying choose the more substituted one in general. Um, the other thing had to do with substitutions. So let's say we did this and I told you it was a substitution, just to make it very clear what we're looking at. We're trying for the substitution here. Well, what kind of substitution does it have to be? Well, I have a charged nucleophile, so I know it's going to be a two. So it's going to have to be an SN2. Now we could argue whether or not this would be an E2, but we're just going to pretend like it's a substitution straight up. With substitutions with SN2s, because this OH attacks at the same time as this leaving group leaves, the leaving group blocks the face that it's on. This OH cannot approach from the side that the leaving group is on. So that means when it substitutes, it has to substitute. Oops. It has to substitute from the backside. That is the only option. But if we compare this to the same starting material, but let's make it an SN1, let's use a not charged nucleophile. What's the difference between SN1 and SN2?
Carbocation.
Right. This leaving group leaves first because this is a bad nucleophile. It is not a good nucleophile. So I form a carbocation first. And since there's nothing blocking the water when it adds in, it can add into either side. So I get a mixture of these two products. SN2 is very stereospecific. It will give you the same thing every time. You will always get the inverted stereochemistry. SN1, because this is just an open orbital, there's nothing blocking my entrance. Well, now I get a mixture. So again, I'm it's good that you can recognize it. This is SN1 and this is SN2, but it's the next step. Okay, there's actually stereochemistry here. What's happening to the stereochemistry? Why is it happening? It has to do with the formation of the carbocation. That means that this water could approach from either side.
On the exam, do you want us to take off that other hydrogen where that's making the positive charge for the last one that we just did?
Yes. So on an exam, I would yeah, let's do that. I'm gonna draw this more suggestively. Right, because we have a positive charge, we don't want to end on a positive charge. I'm going to take a proton. It does not matter what I use. I'll use just water. But we need something to take the proton to leave it as a neutral. As a neutral species. Right, again, this is the next step, right? And the last thing we really talked about was, let's see. Something I've kind of touched on is that alcohols can be leaving groups, but they have to be positively charged. Or oxygens can be leaving groups, but they have to be positively charged. So if I just had a nucleophile, this could not do this because let's say we did it. This is kind of a weird example. I'll do this. The problem is that we formed this negative OH. This is not a good enough leaving group. It is not stable. If we compare that to something like this, we could get this to leave because the Br minus is so much more stable. It's bigger, it's more electronegative, it's able to stabilize that negative charge much better than this OH. This is a bad leaving group. But we can make OHs a good leaving group by protonating them first. So if I have protonated water, if I've protonated an OH, if an OH has an extra proton, well, now this is a good leaving group. It can leave on its own, just like a bromine could. In an E1 or an E2 situation or an SN1 situation. So let's say I had something like this. Let's do HCl. This is a very easy way to install a halogen somewhere. I can substitute, not only can I substitute like up here, like here, I substituted a bromine out for some sort of alcohol or some sort of oxygen. Now we can do the opposite. We can substitute our oxygen out for some sort of halogen. This is the only thing that could get protonated. We form this, which is a good enough leaving group to leave. And then Cl can come in and add. Right, but the principle is the same as an SN1. And if you follow your steps, you should be able to see it. You protonate the alcohol, it turns into a good leaving group, it leaves, then you get an SN1. These will always be SN1s, by the way. Alcohols with some sort of acid.
I had a question on one of the, I don't know if I should wait to ask it, but I had a question on one of the problems from the review. Um, it's the one with the um NH and then the HCl and then the like OH, like there's a carbonyl and I think it's right there. Um, Back up like the second to last one on that page.
Yes, ma'am.
Yeah.
Okay.
Yes.
What's the
I was a
confusion?
little confused because I just was looking at your like the answer,
Yep.
like the final product, and I noticed that the H that was bonded to the carbon that's bonded to the OH wasn't there. And I was wondering where it went.
This is a very common question. This is something that gets people all the time with carbonyl stuff. So, good question. All right. So, these are all thrown in here. So, there's going to be a lot. Okay. Before we get there, let's briefly talk about something. Okay. So, I'm going to use red to be nucleophile and gold to be electrophile. Oh, wait. So, in this first question, what is my nucleophile?
Your nucleophile is going to be um the OH, right?
Yep, the alcohol. What is my electrophile going to be?
The carbon on the bromine.
So, if my electrophile is an alkyl halide, then I'm in SN1, SN2, E1, E2 territory. That's where I stop and I say, okay, we can do four things to an alkyl halide: an SN1, SN2, E1, or E2. But don't be robot mode. Is there an alkyl halide in this question?
No, there's not.
No.
Oh, well,
What's my
there's Cl on the outside, but
alkyl means
that's not one.
carbon. That's it.
Okay.
Yeah,
Yeah,
that's
I'm
an acid.
sorry.
So, do I have a nucleophile here?
Yes, the carbon and the carbonyl.
That's my electrophile.
Oh, yeah. The NH, the nitrogen on that NH2.
That's my nucleophile, right? And I have an acid.
Mhm,
So we're not in SN1,
mhm,
SN2, E1, E2 land. This
mhm.
is this is carbonyl land. All right.
Okay.
Well, I have an acid, and what do acids want to do?
They want to give protons to the nucleophile
They want to give protons to the electrophile.
or the electrophile. Sorry, my bad.
So I want to make my electrophile as good as I can make it. So I'm going to draw everything else the same. All I've done, oh, all I've done is protonated my electrophile. Now my electrophile has a positive charge. This guy is ready to go, ready to react. Then I have my nucleophile still sitting around, right? So I either tend to make my nucleophile really good or my electrophile really good. but I tend to make one of the two charged. Does that make sense? Now I'm making my electrophile charged. Now that it's charged, it's ready for my neutral nucleophile to attack it. And all I do, the only difference I do is what's shown by the arrows. This N bonds to this carbon, which now the O, I broke the double bond and now it's just a neutral OH. There was a hydrogen on this carbon here.
Mhm.
And then 1, 2, none of this changes. Do we agree?
Mhm.
Are you following here?
Yes.
Okay. And then what I probably showed was this. Because I have a positively charged product, I'm going to neutralize it, and I get this. And what I probably drew was this. Correct?
Yeah.
And you're asking
Yes.
where this hydrogen went.
Hmm.
Okay. Here's my question. How many hydrogens are on this carbon?
3,
How do you know?
because it has to fill the octet. Okay, so it's just like an understood hydrogen.
Yeah, it's just implied.
Okay.
For
So
whatever
we can either draw it or not draw it.
yeah, for
Okay.
whatever reason, if it helps you keep track, draw it. It's not going to be wrong. For whatever reason, chemists
Hmm.
like to draw the H out on aldehydes. I don't really like it. I think it confuses people, but it's very common. It's how everybody writes
Hmm.
aldehydes. So I show it to you because that's how people draw it. But this is the same molecule as this. I could equally draw this just like this. And it's the same thing because
Hmm.
that hydrogen is implied.
Okay.
Right. So don't get tripped up because any hydrogen on a carbon can be implied at any time.
Hmm.
So you know that this has one that this carbon has one proton on it because it has to. And it's the same proton as this. We just didn't draw it the second time.
Okay, that makes sense.
Yeah. It's a very common thing that's kind of confusing until you see it a couple of times and then you just know it's implied and we don't have to worry about it. What's really important is that
I
your
was also
carbons stay the same. A lot of people will drop carbons from
okay.
time to time or drop atoms from time to time. Make sure you're counting your atoms, your carbons.
Okay.
What was your
I was
also?
also wondering, yeah, if we have like you know how sometimes you have like a BR or like other atoms floating around in your final product. Um, will we lose credit for not drawing those? Will we lose credit for drawing them? Like, how should we go about that?
Yeah, that's an interesting question. It doesn't hurt to draw them. You notice like I didn't draw the Cl minus here, even though it's still there. Um,
Hmm.
I didn't draw it until I needed it. Is kind of the
Hmm.
convention. Um, but
Okay.
if it has carbon in it, then we typically draw it, unless it was like an acid or base and it's out of the equation. Like notice with eliminations, I don't really
Oh,
draw.
he's going through some of them.
I am going through some of them.
You should go get your food, bro.
You should. See, notice I didn't draw this here, even though this
Hmm.
should be a product. It's really I just used it as a base. Like I'm trying to get rid of it. Like it's not relevant to my answer. So for these, I don't need you to write the
Just do it.
Cl minus or
Nobody's stopping
whatever.
you. This
Um,
isn't the quiet floor. Go to the announcement that he made about it. There should be a link to the Zoom.
um, yeah, someone's talking that's not on mute, so we can hear you. But it's all good. Uh, sorry, that's a good question. Yeah, generally, anything with carbon in it, you're safe to include or not include. But sometimes,
Mhm.
like here with this particular reaction, I needed that Cl minus to explain the chlorine adding in. So don't lose track of it. It's still there.
Okay.
So if it helps to just always draw the Cl minus, and if it doesn't do anything, it's just sitting there. Like it's not any more right or wrong to have it there.
Okay. I also noticed that I don't know if this was a mistake or if this is like something that's actually important. There was a question with iodine and then potassium on the oxygen ethyl reaction, and I think go up, maybe further up. I think it's still up. It might be on the right there on the bottom.
Yeah.
Um, I think there might have been a missing carbon on the answer key. Um, and I wanted to make sure that the carbon wasn't just like going somewhere and I was missing it. Because on the answer key, you have it like the O ethyl group directly bonded to the ring. Um,
Okay. Well, let's do it piece by piece here. All right. What's the first thing I see here?
alkyl and
Okay.
charged base.
Right. I see the metal and I see an alkyl halide. So I know what my nucleophile and what my electrophile are. We have a leaving group. We're in SN1, SN2, E1, E2 world. Okay.
Mhm.
This is charged, so it's a 2 straight up. And then this is a primary alkyl halide, so it's an SN2. So I'm just getting a straight substitution. That should be my answer. Did I miss a carbon from this answer?
Yeah,
Okay. Yeah.
that's what I figured had happened, but
Yep.
I just wanted to check.
This is it. So disregard what I put
Okay,
before.
awesome. Thank you.
No, good question. Glad to clear that up. I'll fix that when we're out of here. All right. Any other specific questions, or I can just start going through these one by one.
Can you
Well,
go over how to differentiate between a elimination and substitution reaction whenever heat isn't denoted?
Okay. So there's a couple different ways, right? So let's look at this guy. There's no heat. Well, actually, I mean, there's a lot of examples, right? So there's no heat involved. We have sodium hydroxide, draw out the ionic. This is charged, so it's a 2. And then I've got a tertiary alkyl halide, so it has to be E2. This nucleophile cannot get into that carbon. So I have to do an elimination. So for charged things, it's pretty straightforward. You're just going to look at um, is that a primary, secondary? Is that a primary, tertiary alkyl halide? If it's tertiary, it's E2. If it's primary, it's E1 or SN2. Sorry. For something like this one at the bottom, well, now we're dealing with ones because this is not a charged nucleophile. So it has to be a 1. It has to either be an E1 or an SN1. For these, if I do not specify heat, I am looking for an SN1. Even though it's a tertiary, SN1, SN1 and E1, it does not matter if it's secondary, tertiary. There's no favorite there. It is only heat or not heat. So since there's no heat, I'm gonna assume this is an SN1. Either way, you should know it's a 1, and you should know that the first step is this. Like that should just be automatic because it is a not charged nucleophile. Does that make sense?
So whenever it's 1, you assume it's substitution unless heat is denoted.
Yeah, that's a fair way to say that.
Okay, thank you.
If it's a 1, assume it's substitution unless heat is denoted. I like that. So we get the substitution. There's no heat noted. So the thing, this is what we were talking about earlier, right? Because I'm adding into a carbocation, this can either add as a wedge or it can add as a dash. It can be both. Well, it will be both. You will get both. So we've got a charged product. We're not going to end with a charged product. Going to deprotonate. And we get that. Same thing happens over here. And we get just the OH. So we get both of these products. Or alternatively, you could just do this deprotonation on one of them, and then at the end just say it's racemic, which means that I get a mixture, a 50-50 mixture of both products. I'm cool with both answers. As long as you make it clear, you know that, hey, this is going to be the wedge and the dash OH addition.
And for twos, are only tertiary favored towards elimination, or is it also secondary?
So yes, secondaries favor elimination with twos. The only time that's not true is something like this. There's some nucleophiles that favor substitution. So you see potassium, gonna draw a ionic straight up. First thing I do. That's my nucleophile. I have this alkyl halide. That's my electrophile. These two atoms are going to interact with each other. So it's charged. So it's a 2. It's also ugly. It's charged. So it's a 2. And then one thing that comes up pretty often is these tend to be better nucleophiles than bases. So if you see something that looks like this, a negatively charged sulfur, a negatively charged what's called a carboxylate, which is just a deprotonated carboxylic acid, we're looking at a substitution, even on a secondary. But if it was NaOH or something with just an O minus on a secondary, then it's going to be an elimination more often than not. So this is nucleophile effects. What is acting as a nucleophile can affect what you get. So yeah, this is going to add into here. And I get an inversion of stereochemistry. Notice something. I can throw all of this junk on there. It does nothing to the reaction. It is just distractor. That is the main way I can make a question harder. Is if I just make it this huge, ridiculous molecule that has nothing on it, it doesn't change any part of the question. I want your eyes to look for heteroatoms. I want them to look for carbonyls, for metals, for things that aren't carbon. Another common thing that's put in as a distractor is these ethers. They are not reactive. They are not alcohols. They are ethers. There's a reason we have different names for them, and it's because ethers they're not nucleophilic. They don't do anything. So they're kind of a safe bet to put on there. But yes, to go back to the original question, in general, on secondary alkyl halides for twos, E2SN2, it's going to favor elimination unless you have one of these specialty nucleophiles. So you're good for something that looks like this on the test. I'm not going to be too sneaky about it. What's up?
I have a question on like the problems that are separated by a plus sign, like where you have two compounds and then it is applicable to E2, SN2, stuff like that.
Yes.
Yeah, that's what I'm looking at actually.
Yes.
Is it always going to be SN2 or the two that you put on there just so happens to be SN2?
Let me think. Yeah, I mean, it doesn't have to be SN2, but it wouldn't make sense to have a third thing if you weren't doing SN2, if that makes sense.
Okay, yeah, that makes sense.
Like
So
if
when you see a problem, oh, I'm so sorry.
okay,
When you
well,
see a
actually,
problem like that,
yes, okay,
are
continue.
you always going to start if there's two things and then like a base or nucleophile, are you always going to start by making the nucleophile better and then doing the like SN2 E2 thing?
Okay, let's talk about it.
Oh,
Uh, where's another example? Yeah, notice something. I did the same thing. So, okay. I'm going to give you another reaction that doesn't follow this format. If I did something like this, mm, clean this up a little bit. Do you see this?
yeah.
All right, so we still got to go through our steps, right? So we have that. So it's charged. Then what is this?
Um, but it just act as a base.
Well, this would be a very bad base, right?
Hmm.
Where this is a very good base. How do I know that?
Because of the charge, the oxygen is charged, and the
Right,
one
exactly.
on the left.
The sodium methoxide is what it's called. Is a
Mm.
better base than um this methanol. But what is this playing in this role? If it's not acting as a base, right? Because this would act as a base way faster. What is it doing?
Is it making the electrophile more like a better electrophile?
No. I mean, it's not particularly. It's not an acid. It's not acidic.
Mm.
I mean, you do see an acidic proton here, but that would be taken by. Do me a favor. What would happen if my good base was to take that acidic proton?
It would become a nucleophile.
Sure, I would get HOCH3 and COCH3 minus. What does that look like?
Um, I have no idea.
Looks like exactly what we started with.
Okay.
Do you see what I'm saying?
Yeah. So then you just get caught in a.
Well, it doesn't do me anything, right? Yes, that
Mhm.
happens. These probably share protons with each other all the time, but it gives me the same thing back. So in this case, this actually is our solvent. It has nothing to do with the reaction. It's a good
Okay.
solvent to have because if it gets deprotonated by the base, well, then I just regenerate the same base. Like it just goes back and forth. Does that make sense?
Yeah, that makes sense.
So this has nothing to do with the reaction. It's just my solvent. So just because there's three things doesn't mean that each one is important,
Okay.
right? This bad base or the good base, this charged base takes precedent over the uncharged base. It's just a solvent. Sodium methoxide, this thing is a solid at room temperature. So you need a solvent to dissolve it in. Sometimes you use the conjugate acid of that base, which
Okay,
is
that makes sense.
okay. It's charged. We've got a two
Hmm.
straight up. What kind of alkyl halide do I have?
Tertiary.
Okay. So what am I going to get?
Uh, E2.
E2. So do I take proton A, proton B, or proton C?
Proton C.
I have to, right? It's Zaitsev's rule. So I end up getting this. Right. So the number of things before, after, or during an arrow have nothing to do with what kind of reaction you have. I can make up
Okay.
all sorts of things. I could dissolve this. I could do the same reaction and write it like this. I mean, you'll see this sometimes. Right? Like where just a ton of things are listed, but these are all solvents. Like they don't do anything. thing that's important is the thing that has a big old charge on it.
Okay, that makes sense.
I'm gonna move this out the way. I'll put them over here. All right, that's a good question. But yes, for the most part, like notice here, this is a good base. Like, okay, here's another hypothetical. Let's do the same reaction, but now are a similar reaction. Let's make it pretty clear. Let's say this is my reaction. What's going to happen?
Um, is the KO butyl going to the electrons on the O? Well, I would separate the, so K positive, O has a negative charge of electrons.
Sure.
And then I would give the
Yep.
would you give the electrons to the okay, sorry, I have no idea what to say.
I think you're on a good path. I've got a base. I've got, what does this look like to you?
It's a nucleophile.
Sure. And I've got an electrophile.
Mhm.
What's going to happen?
The electrons should go to the electrophile, and that would act as the nucleophile.
Okay. So you can think of this as one of two things.
Mhm.
Either this base is going to activate the nucleophile, and I'm going to get this, or it can act straight up like a base. And do an E2.
Does it matter which one you do?
No, because let's say I didn't do this. So I didn't do this E2. Well, now I've got a nucleophile and I've got this. Right?
Yes.
What's going to happen? I've got a charged nucleophile. What is it?
The O negative, it's going to go to the carbon attached to the Br.
Well, let's think about it. I've got a charged nucleophile. So it's going to be a 2. Right?
Yes.
What about my alkyl halide?
It's tertiary, so it's going to be E2.
Has to be an E2. Then am I going to take proton 1, 2, or 3?
3.
So I form the same product either way.
Okay. I think that's where I was struggling because like on when I did the practice test, I would do the 2 steps that you did, but the opposite way. And then I thought that I was doing it wrong. So it's you can do it either way as long as you use the same product.
Well, no. This one's a little different. You do the acid base first.
Okay.
In this case, so how this case is different. All right, so I've got a base. I've got a nucleophile and I've got an electrophile. Do we agree?
Yes.
All right. So I've got a strong base. That means that I have to watch out for eliminations, right?
Yes.
Right? I'm this thing can act as my base. Can I do an elimination on this alkyl halide?
Not currently, right?
Why?
Because is it because there's not like a charged nucleophile? I don't know.
I mean, it could be my charged nucleophile. Could I do an elimination on this electrophile if I wanted to?
Like right off the bat, I guess, yes.
Okay. Show me.
Would you take the, oh wait, no, there's no room for an H on that
There's no
carbon.
H's here, right?
Yeah.
I can't do an elimination even if I wanted to.
Okay, I see what you're getting at.
Right. So I kind of limited your choices.
Hmm.
To be honest, what I'm showing here on the right, no one's going to do this. Like practically, yes, you're right. If I show three things, it's going to be more likely to be an SN2 than anything. But that doesn't I still want you to follow the steps. I don't that's not something I think is very useful moving forward.
Okay,
Counting
got
how
it.
many reactants are there and saying it's got to be an SN2. Because that can be
Okay.
tricky. That can get you into a bad situation. So if I give you a nucleophile, I give you an electrophile, I give you a base, deprotonate your nucleophile, then attack it.
How do you know
Okay.
there's no hydrogens?
Okay. Let's say I'm doing some elimination on this. Yes? Following?
Yes.
Whoever asked me the hydrogen question. So, in order to do an elimination, I need to have room on both of these. I need to make room for both of these carbons, right? Carbons can max hold 4 things. So, I need to remove a bond from each side. Well, this side's going to be my leaving group. That's the thing I'm going to remove from that side, right? So that means that this carbon needs to lose a bond. So the base takes a proton and we leave behind those electrons. That explains how I have 2 hydrogens on both carbons in this case. So I need a hydrogen that's 1 carbon away from my leaving group. Do you agree?
Yes.
All right. So this is my leaving group, the Br, and this is the carbon that the leaving group is attached to. So I need to go 1 carbon away from that leaving group, which would be this carbon. Do you agree?
Yeah.
How many hydrogens are on that carbon?
None.
There are no hydrogens, so I could not do an elimination even if I wanted to. Because there's nothing coming off of that carbon.
Thank you.
Yep. It's a common question. People will just get in robot mode and draw that doesn't exist. That's not there. You can't, you actually could not do an elimination on this even if you wanted to. In a way, this question, notice what I've done here is when I added complexity with the base, I simplified what you could have possibly given me. There's no room for it to be an elimination. So it has to be a substitution. I'm not going to like give you one that could have 8 different answers. I guess let's finish this while we have it. I have a base. Bases take protons from nucleophiles. Then I have, move this guy. You guys can zoom in. Then I can do this. I've got a nucleophile. I've got a good electrophile. He's charged, so it's a 2. My electrophile is a primary alkyl halide, primary leaving group, so it's going to be an SN2. So I do the kickoff step at the same time that I add the nucleophile, and I get this.
I have a question.
Yes.
How did you know to not, because in mine I got the same exact answer, but instead I took the electrons from the oxygen from the OH and I attacked the bromine, and then from there I used the acid or the base. Like, how do you know to use the acid or the base instead of using the two things that you have to the left of the arrow first or to get
All right, so that's a kinetics question. So the answer to that is that acids are protons are really small, and the addition and removal of protons is very, very, very fast. Like, you put an acid and base together, it takes no time to find an equilibrium, right? Have you ever poured vinegar and baking soda?
Yeah.
It is immediate, right?
Mhm.
That acid base reaction happens like that. That transfer of protons happens like that. These nucleophile electrophile reactions take more in the time course of minutes to hours to sometimes days. So in general, acid base is going to be super fast, especially I'm going to give you strong acids and strong bases.
So then
So
my first step should always be to look at the acid or the base and then go from there to attack something else before I bring those
always,
back together.
yes,
Okay.
there will be exceptions at some point, not in Orgo 1, and honestly, not even usually taught in Orgo 2. But yes, if you have like a weak base in an amine as your nucleophile, then sometimes the steps are reversed. But that will be something I clearly make note of if we ever talk about it. For your purposes, do the acid base first.
Okay. Thank you.
Yep, that's a good question.
Will there be any like acid and base type questions like the ones that we had on the quiz for that unit?
Yes. Okay. Yeah, I forgot to put that on here. I've made those questions actually. I just didn't post them, but yes, there will be ranking acids and ranking bases as a question.
Do you think you can post those practice questions?
Yeah, I'll post them.
Thank you.
But there's only so many questions I can ask, and they look a whole lot like the quiz. So I'd go back and look at your quiz from 2 times ago. It's not going to be a big part of the test, honestly. Questions that look like this are probably going to be, you know, a third of the test, maybe a quarter of the test. I haven't done the math out on it, but this is going to be a big portion. Can you just follow arrows on reactions you've never seen before? This is a skill that I put a big emphasis on because, when we're drawing arrows down here, if you're just memorizing arrows you've seen before and not understanding what the arrows are actually saying, then we've lost. So I want to really make sure I'm going to put a huge penalty on you understanding what it means to push electrons. That's going to be a quarter to a third of the whole test. You don't even have to know any reactions. It is just, can you do this skill that we've practiced every single day?
I have a question
What's up?
for the one that's at the top of your screen right now. When I first tried to do it, the one at the OH, it's like half of a ring. Yeah, the second, yeah, that one. When I like tried to do that, I didn't understand that it was creating another bond. Like, how do you know that? Because I had just drawn it that like E minus would be on the side. Like, I don't know. I just didn't necessarily immediately understand what that meant.
Yeah, okay, that's a good question. I might be, so you'll see it written both ways, where either this arrow goes here or it goes to that carbon to show that it's forming a bond. Um, but you'll see this too. This is pretty standard terminology. If I wanted to end on the carbon, I would very specifically tell you to end on this carbon.
I didn't even like draw it on the carbon. I just drew like an E minus like floating in the around.
Oh no, that's not a thing that ever exists. So what this is trying to show is that hey, these electrons end up literally here. But you'll see it both drawn like this or drawn like this. Both would technically be correct. Um, so yeah, that's trying to show that hey, these electrons are ending in this spot where you can imagine a bond between these two carbons. Did you understand the other electrons? So you were able to get, so you drew
Yeah.
something like this.
Yeah, that's what I did.
Well, that would put a positive charge on this carbon if you wanted to be pedantic about it.
Yeah.
Which is like, well, it would also put a positive charge on this. It would, if you wanted to do that, it would be this. Because this arrow shows a movement of two electrons.
Yeah. Okay.
So then at the point you have this, you would have two electrons floating by some very positive carbons. And it just would make more sense for them to share the two electrons. But that's what this is trying to show, that hey, these electrons are going here to this bond. That just hasn't been drawn yet. But yeah, that's a good question. And this is a tricky one. It's actually called a cope rearrangement. You might learn about it in Orgo too. But if you don't understand what the arrows are saying, then yeah, it's a that's a good question.
I have
These
another question.
Yeah, what's up?
Um, I understand like that nucleophiles and like or like bases make nucleophiles better, but when you refer to things as like being a nucleophile versus a base, like how do you know whether it's a nucleophile or if it's a base?
That's that's organic chemistry. That's the big question. Um, it's a constant conversation. The short answer is we have things that are basic that don't like to be nucleophilic, if that makes sense. So if you think about what was the difference between a substitution reaction and a elimination reaction. Substitution, you're trying to get into a carbon, you're trying to do a nucleophile electrophile reaction. Elimination, you're taking a proton, it's an acid base, it's a base. So how do I prefer, let's say, an SN2, or how do I prefer an E2 over an SN2? What's the difference there?
It's like bulky, so you can't do a substitution, you have to do an elimination.
Right. So if I make something really bulky, it will never act as a nucleophile. It just can't. It just won't be able to do it. So it will only do the job of a base. So you'll see me write this a lot, right? It's a big bulky base. And we talked about this today a little bit. Another really common one, you'll see this pop up um, in Orgo 2 a lot, used as a base and not a nucleophile. It's because what this stands for is lithium diisopropyl amine. That's what LDA stands for. But you can see that this thing being so bulky means that it's very unlikely. Like if I put LDA or potassium terbutoxide with this electrophile, nothing would happen. They wouldn't react with each other. They would be too bulky to do a substitution, and you don't have a proton to do an elimination. So people use these big bulky bases as a way to not have to worry about acting as a nucleophile. Does that make sense?
Yes, thank you.
No, it's a really good question. For whatever reason, I don't have a great justification for this, but sodium hydride is the same. Sodium hydride never works as a nucleophile. There are hydrides that do work as nucleophiles, and you'll talk about that in Orgo 2. Like a hydrogen attached to a metal that acts as a nucleophile instead of a base. But for now, sodium hydride, even though it's not bulky, it's actually incredibly non-bulky. It only acts as a base. So that's just one you know. I'm going to try to make it kind of obvious.
Okay, thank you.
Yeah, but that's a good question. It is a constant conversation about base and nucleophiles, and every time you learn a new reaction, you should ask that question: why is this acting as a nucleophile, not as a base? Why can't it do this? If you have take Orgo 2 with somebody that's not me, and you ask those questions, they're going to just think you're the smartest person ever. They're going to be like, this undergrad cares so much about organic chemistry. But there is a fundamental similarity between nucleophiles and bases. And understanding when one acts as a base versus a nucleophile is just a continuing project we're always going to be talking about.
Quick question. Can you open up the quiz 5?
I would love to open up the quiz 5. I still have some people retaking it.
Okay.
I will open it up before I will open up tomorrow at some point. But I need those people to retake their quiz.
Okay, thank you.
But yes, I do really want you guys to get that so you can see kind of some of the mistakes you made. Because I think hopefully you can look back on them and think, oh, that was a silly mistake. I shouldn't have done that. All right. Any other specific? I feel like this has been a really good conversation.
I had a quick question about the one with the different resonance structures with the rings. So when I did that the first time through, I ended up drawing 5 resonance structures total, and the answer key only showed 3. So my question was just when do you know that you're
No,
okay?
you're right. The answer key was wrong. There should be
Oh,
5. Yeah, if I'm honest, I did this really fast and I was thinking about benzene, which only has 3 resonance structures, but you're right. This one has 5.
okay, perfect. Thank you.
You can push that positive charge to any carbon on the ring.
Right.
And by the way, I do want you guys showing the arrows. So I'm going to make this more clear on the test. I'm going to say draw all the resonance forms and the curved arrows to get there.
For the one above that, when it says resonance structure like over 3 atoms, what does that exactly mean?
Okay,
Or
yeah. So I just wanted to be clear because I did show something like this where you can draw this resonance structure, and technically this is a resonance structure. Um, but it's only across two atoms. So I really was just I wanted to make it clear that I'm looking for you to see that this sp3 carbon is interrupting the resonance between the double bond and the carbonyl. Right. So when I say over three atoms, I literally just mean that you can't you can make an argument that resonance it's just a way to make it really clear that hey, this has no resonance.
Okay. Thank you.
Because you can argue that hey, if I push this one up in the carbonyl, it doesn't work. But it's mostly for me to just see if you understand that, and it should just be easy points.
Can you show how the other two have resonance? That looks really right.
Well, this one has resonance because it can push here. Right? There's three carbons that can share that charge. Again, there's three carbons that can share this charge. This guy I can't push into a third carbon because this is sp3 hybridized. It cannot take a double bond. So
Okay,
this
I think I was looking at it like the arrows are there being three different movements, not necessarily the
no, it's about it's so I'm sharing this charge over three different carbons, three different atoms. Here I can't move this. This doesn't work because this is sp3 hybridized. Here I can move this up in here, and now we're actually sharing the charge over four different atoms.
Okay. Okay, thank you.
Yep. Yeah, resonance, as you guys have noticed, is one of those things where the more you can get the concepts down, the more you can understand the concepts. What does an acid do? What does a base do? How do I stabilize charge? Um, what is a nucleophile, an electron donor? What is an electron acceptor? Like those ideas feed into everything. Like every reaction we talk about, you can think of in terms of, oh, do I have an acid? Do I have a base? Do I have a nucleophile? Do I have an electrophile? How do I stabilize charge? What is the most stable place for a charge to be? And that's how you're gonna that's how you can justify every single one of these reactions. And it makes the memorization a lot smaller. Does that make sense? Like the more you can think, it's hard to do. It is not people's first instincts. Their first instinct is to be like, what is this product? I'm just going to draw the product and work my way back from there. There's actually studies that show that students want to draw a product and then work their way back. But if you can teach yourself to work forward, teach yourself to reason and justify how a mechanism works, the things that cause something to work, it's actually predictive. So if you get good at it, if you get good at drawing mechanisms at these curved arrows, if you get good at seeing these patterns, you can start to predict reactions you've never seen before. And that's my goal for you going into organic 2. You're going to be thrown a million reactions. My goal is you can start to predict things. You can say, hey, this looks nucleophilic. This looks electrophilic. That's an acid. I think the flow of electrons is going to go like this without ever seeing the reaction. Like I hope that when I showed you this reaction today, I know we didn't have as much time as I wanted to. I hope your first thought was, I've got an acid and I've got something with electrons. I only have one thing with electrons. There's only one place that will be protonated in this. I hope without me saying anything, this was your first instinct. It is the only thing that makes sense. And then what we added on to that makes it simpler, right? Oh, this OH2. I know that positive charge doesn't want to be there. I want to give electrons that positive charge, and it would be relatively stable. Now I've put a positive charge on a carbon instead of the oxygen. That carbon can hold a positive charge better than an oxygen because it's less electronegative. It's more electropositive. Well, I've got a negatively charged bromine now. That looks like a decent nucleophile, and I've got a great electrophile sitting around. Right? If you can reason through why these things are happening, well, when you get to a reaction that you've never seen before, try to think about it. Do I have acids? Do I have bases? Do I have something nucleophilic? Do I have something electrophilic? And do it step by step. Where are the electrons? Where are they going? Does that make sense? That's the question you ask every step. That's an acid. It's going to get protonated. Oh, that's a positively charged oxygen. It's probably going to want electrons. And that makes a more stable carbocation than what I had before. And now I've got an electrophile. Right? These are the thoughts. This is the conversation you should have in every reaction. Does that make sense? It's about training your thoughts, not just having the right product, but having productive chemical intuition.
Would that one you just did be S1 then?
Yeah, this ends up being an SN1. Very common SN1.
I have a question. Could you please do one of the problems where it doesn't result in any reaction, like where it says Na?
Oh, that's not no reaction. It's just not an SN1, SN2, E1, or E2.
Yeah, like I meant like those. Like I know they have a reaction, but I'm not sure how to do them.
All right, stay on the line with me. You there? Let's do
Yeah.
this one. Do I have a nucleophile?
No, I mean unless like the OH
Yeah,
is
that's a nucleophile to
oh,
me.
okay, yeah.
Yeah.
Mm-hmm.
Do I have an electrophile?
Yeah.
Where?
The O with the double bond, like the carbon at the
Perfect.
end of the double bond. Yeah.
Yeah, that's awesome. Do I have an acid or a base?
Yes.
What do I have?
An acid.
Do I want to protonate my nucleophile or my electrophile?
Um, I don't know. Like that's kind of what I'm asking.
Okay. Well, what do protons do? Are they positive or negative?
Positive.
So if I want this reaction to happen,
Hmm.
this is a neutral nucleophile. It's not any good. It's not a very good nucleophile, right? This is a neutral electrophile. It's not very good. I have they're both mid, you know? They're not
Yeah.
they're not very good at their jobs. I'm not super excited about giving electrons away and taking electrons. So the acid and base helps make that happen. Does that make sense?
Yes.
So if I've got something that's an electron donor and something that's an electron acceptor, and I want to make one of those two things better at their jobs to get them to share electrons with each other, do I want to make the electron donor more positive or the electron acceptor more positive?
The electron donor more positive.
Well, if I make the electron donor more positive, do you think it wants to give electrons away more or less?
Sorry, can you repeat that?
Okay. So this is a nucleophile, right? Let's play this game. Let's protonate the nucleophile. Do you think he's going to be jazzed now to attack my electrophile?
Yes.
You think this, what does this positive charge say?
That it's missing electrons.
So do you think it now wants to give away electrons?
No.
No, that doesn't really make any sense to me.
Mhm.
Does it?
Yeah.
No, you should never have an arrow flowing away from a positive charge.
Yeah.
Does that make sense?
Mm-hmm.
So that doesn't work for us, right? We want to get the nucleophile to attack the electrophile. So this is not working. So let's try protonating the electrophile instead. Does that make sense?
Yeah.
Well, now look at it. Now, if my nucleophile were to attack my electrophile, we could push electrons into a positive charge. That's a way better situation. Does that make sense?
Yeah, I see it now. Thank you.
Right? I want to make the electrophile positive so I can get this reaction to happen. And now I've got a positively charged product. That's what this comes in. I'm going to just deprotonate this product to get rid of that positive charge. We're done.
Okay, yeah, I see how you did that. I was just confused just looking at it on the like answer key. Thank you.
No, that's a good question. It's one that gets confused because yes, you think the electron donor would want to go get a positive thing, right? And it does. That certainly happens, but that kills the reaction. That keeps the reaction from happening. So we're trying to incentivize the nucleophile to attack the electrophile.
Yeah, and then also when it says like then H2O or then something, does that mean that that something is gonna like deprotonate
Yeah, that means
something?
that I'm telling you, hey, this is going to end with a charge. Get rid of the charge.
Okay, so it always means like that it's gonna deprotonate. Like there's no other meaning for the then H2O.
Well, it could also protonate. So let's see. Yeah, I don't have any examples, but all right, let's do this. Uh, let's try that reaction. All right. Do I see any nucleophiles in this picture? Do I see any electrophiles in this picture? Well, this carbonyl's got to be an electrophile. It's got to be. It's on our chart. That means I'm probably looking at something over here being my nucleophile. I've got magnesium here. That's a metal. So my first thought is I'm going to draw the ionic species out. Well, that looks like a nucleophile to me. It's a negatively charged carbon. So nucleophile attacks the electrophile, pushes the electrons up, and I get something that looks like that. You can draw this hydrogen or not. It doesn't matter. It's implied. It's got to be there. So I can't be done yet. I've got to charge species. So that's when then H2O comes in. So water's cool because it can act as a base or an acid. So in this case, what do I need it to act as in order to make my molecule no longer be charged?
An acid.
Acid. It needs to give a proton. I end up with this. Right, that's the reasoning step by step. So sometimes water will make my positively charged thing neutral. Sometimes it'll make my neutral thing or my negative things neutral. You just have to decide, is this going to take a proton or give a proton?
Is this an SN1 reaction or?
This is an addition reaction.
Yeah.
So it's none of the above. It's not an SN1, SN2, E1, or E2. Because if I look at this oxygen, right, the oxygen's still here. It was never substituted. It was never eliminated. It's still on the molecule. The only thing that's happened is I've added these three carbons. Oh, I'm missing a carbon. So this is what's called an addition reaction. We haven't gone through the specifics of these. That's for Orgo 2 to do, but right, you know how I taught you guys, I showed you how to do reactions with alkyl halides, and then I said, well, actually, it gets a little bit more complicated. It's not always substitution. Sometimes you do this thing called elimination. That's how the rest of this class can work. You're going to be shown a reaction. You're say, okay, more often than not, this works, but sometimes it doesn't.
Okay, thank you.
Yep. I don't care that you know that this is an addition, but I do care that you can say, hey, this is a nucleophile, this is electrophile, nucleophile attacks electrophile. Then I make it neutral. But yes, then water doesn't always mean that you're making something, you're taking a proton. Sometimes you could be giving a proton with the water. All right. These are great questions. Do you guys, are there any more questions?
Can you review on how to rank acids and bases, like which is stronger and which is weakest?
All right. So we have to remember that acid base reactions are in equilibrium. So let's say I've got something that looks like So if I said rank acidity, and this is a hard one. This is about as hard of a question as I could give you. So when we think about acidity, we think about how stable is this thing going to be once we remove that proton, right? Because that's what protons do. They give, or acids do, they give protons. So if I were to take each one of these protons, what would it look like? What is the conjugate base of each of these things? That's what I want you to think about whenever I give you this question. What does the conjugate base look like? This conjugate base looks like this. I removed a proton from that carbon, so it's got a negative charge. This conjugate base looks like this. This conjugate base looks like this. This conjugate base looks like this. Do we agree?
Yes.
Right. So that's what I want you to do first. Draw the conjugate base out. Then we have to think about the factors that stabilize these charges. What factors are stabilizing the charge of this first guy?
Resonance.
Well, yeah, there's resonance. I can push these electrons up into here. Does this have resonance? Yeah, I can push these electrons up into here. Does this one have resonance? The third one? No, I can't push these electrons anywhere. That does not happen. Does this guy have resonance? Yes. Okay, so automatically I can say that this is my least acidic. I cannot stabilize the negative charge through resonance at all. It's on a carbon. It's not acidic. Period, point blank, will not be acidic. It is on a carbon that has no resonance. Then I can look at the resonance forms of the other things. This first one is sharing a negative charge between a carbon and an oxygen. The second one is sharing the negative charge between two oxygens. And the third one's sharing a negative charge between two carbons. Can carbon or oxygen hold a negative charge better?
Oxygen.
Oxygen. So what's got the most stable negative charge?
The charge shared between the two oxygens.
Yep. Then the charge between an oxygen and a carbon, and a charge between two carbons. So this is about as hard as it could be. You've got to draw multiple resonance structures. You've got to think about the electronegativity of where the charge is at. It's usually a little bit more straightforward than this.
Okay, that makes sense. Thank you.
You can do the same thing with basicity. Let's try some. Oh, the only one that this one doesn't really talk about is hybridization, right? That's going to be more stable negative charge than that. SP is more stable than SP2. For basicity, uh, basicity is kind of hard to think about. It's kind of the opposite, but not entirely the opposite. All right, so bases take protons, they need negative charges to do it. So when I'm looking at basicity, I'm actually looking at what is the least stable negative charge? What are the least stable electrons? Does that make sense? Which electrons want a proton the most? Well, this guy's got to be last. It has no electrons to even take anything with. There's nowhere I could put a proton on that molecule. Then this guy's got a lone pair but no negative charge. So I'm going to automatically put him at fifth. A negative charge thing is going to more want a proton. Then the comparisons between a carbon, oxygen, carbon, and nitrogen, all with negative charges. What is the most stable negative charge there? See if you're awake.
Is it the one with the nitrogen on the nitrogen?
Well, what things like holding onto a negative charge the most?
Would it be the oxygen?
It's got to be the oxygen. It's the most electronegative. So this is going to be my second worst base, or third worst base. Then the nitrogen is better than the oxygen, but worse than the carbons because it is slightly more electronegative than carbon. And then these two are tricky. We just talked about it up here. What's the more stable negative charge? The sp carbon or the sp2 carbon?
For the acids, it was SP.
So the sp is more acidic, which means it's less basic.
Okay.
This negative charge is more stable than this negative charge. So it goes 2-1. So when you're ranking basicity, you're essentially doing the same thing as ranking Acidity, you're just thinking about it backwards. The only weird thing is like a carbon that has no place to put an electron or put another proton. Like this could not hold another proton. There's nowhere to put it. So it's essentially the same idea backwards. Just how stable is the negative charge? If it's stable, that means the conjugate acid was really strong, but the base is really weak. Nitrogen's usually a good enough base that even neutral nitrogen can act basic. You'll see a lot in reactions moving forward that something like this, pyridine, is used as a base with not being charged. Just the neutral pyridine is used as a base because nitrogens tend to be pretty basic compared to oxygens. And this guy's not really nucleophilic. Like we were talking about earlier, he's kind of bulky enough that he's not going to want to get into a carbon reactive site. So he can be pretty safely used as just a base and not a nucleophile because he's bulky. That's really the key. If something's bulky, it will only be a base. And so we can use those selectively to make the nucleophile we want to add in more nucleophilic. All right, any other questions? I feel like this has been productive. Yeah, I would. All right, so here's some suggestions of mine. Depending on where you're at, if you struggled on the last quiz and still don't understand those concepts, I would go back and do the nucleophile electrophile extra practice that I posted at the end of last week, last Thursday. That's step 1. Get nucleophile electrophile down. If that's all you know going into this test is how to do that worksheet, and you just assume everything's SN2, then you're gonna at least be able to nickel and dime your way to like a 50 or 60. Then I'd move on to the lecture 19 packet, the SN1, SN2, E1, E2 differentiating. Right? Okay, I've got an alkyl halide, I've got a leaving group. What kind of reaction is it? It's not always just a substitution. It could be an elimination. We need to watch out for eliminations. We need to watch out for SN1s, E1s. If you get that down, then I move on to what we talked about today. Okay, I know we're doing an elimination, but what side do I eliminate from? How do I know what elimination product I get? Okay, I know I'm doing a substitution, but I see that this on a wedge. So what am I going to get? Am I going to get a racemic mixture, or am I going to get an inverted stereochemistry based off of SN1 or SN2? Right? These are like if you're feeling pretty good. If you're like, I was at an 80, like if you don't know these concepts, you'd probably get a 70 or an 80 on the test. But they're less important. The priority goes down, right? If you only knew these concepts, you'd fail. You've got to build from nucleophile, electrophile, arrow pushing. Oh, wait, this is wrong. Start nucleophile, electrophile, and arrow pushing. Make sure those concepts are solid. Then you can move on to E1, E2, SN1, SN2. Then you can move on to Zaitsev's rule, inversion of stereochemistry, using alcohols as leaving groups. Although I probably know that alcohols could be leaving groups when you're learning through SN1, SN2, E1, E2, that I could just use OTS, OTMS, whatever, and it's the same thing as a halogen practically. Okay. If you are still kind of worried about SN1, SN2, E1, E2, I put an active out there that has a couple of like kind of tutorials that I think is pretty helpful. And it has more practice problems with that stuff that I checked through, so you can get a little bit more practice with it. And I tried to mix in the occasional carbonyl thing because I don't want you to be in robot mode. I want you to be able to fluently see these reactions as what they are and not just assume everything's got to be E1, E2, SN1, SN2, because you're going to get these next semester just randomly. They're going to just be like, all right, and then this is an elimination, and then this happens. And you're going to be like, whoa, whoa, where did that come from? So I want you to be fluent in it. I want you to be able to see what it is without me priming you for what it is. Fair enough? Cool. Well, I'd happily take any other questions if you think of one in the next 30 seconds or so. But if not, then I will shut off this recording and see you guys for office hours tomorrow.
Sorry, I have one more question. I'm not sure if you went over this already because I joined a little bit late, but I was wondering if you could do one more problem talking about racemic reactions.
Okay, so racemic is going to happen anytime I have an SN2. So anytime I form a carbocation before I don't have an SN2 on here. But or sorry, anytime I form a carbocation before substitution, so an SN1, I will get a racemic mixture.
So it's SN1, not SN2?
SN2 very predictably. So let's say I had this. Actually, oop. Let's do. Wow, worst benzene I've ever drawn. All right, two different reactions. The top one, do I have a charged or non-charged nucleophile?
Is the top one the hexane with the nitrogen?
No,
Like, which one are we looking at?
the things I just
Oh,
drew.
okay. Okay. The alkyl halide is primary, but there's not a
This
charge.
alkyl halide is secondary. The alcohol has no charge. Yes?
Yeah.
So what does that tell me?
You need to like find a charge another way.
No, not necessarily. I mean, I guess this is going to be a 1. It's going to be an E1 or an SN1 because it's not charged. This one down here, there is a charge because there's a metal. So it's going to be a 2, an E2 or an SN2 right off the bat. You agree?
Yeah.
Okay. Well, realistically, these could be anything. I haven't specified heat. So we're just going to act like these are both substitution. Let's just say they're substitution, which is a reasonable thing. There's nothing really differentiating them from eliminations here, but substitution. So with SN1, I get the formation of this carbocation, which means when this alcohol adds, it can add either direction, right? There's nothing blocking this alcohol from either being a wedge or a dash. It adds in both ways. But this SN2, let me just erase this. This happens all in one step. So this oxygen has to attack from the backside to kick off this chlorine. It cannot approach from the wedge face because the chlorine's there. It has to approach from the opposite side. So when it substitutes, I get this. I exclusively get the dash version with SN2 because it approaches at the same time that the leaving group is still there. So leaving group is blocking the face, the wedge side. So it can only add the dash side. But when I have a carbocation, when the leaving group's already left, it can approach from either side.
Okay, I understand. Thank you.
Yes. I also saw some people before. I do want to make this clear. It is very important that when you do an E1 or an SN1, that you form the carbocation first. The formation or not formation of the carbocation is essential in the difference between SN1 and SN2. I would rather on the test, I don't care if you know exactly if it's an S, like what it's called, but I do care that you know how the chemistry works, that you form the carbocation.
Do we have to draw the carbocation like with the positive charge and then like do each step, draw it out, or like would you want to see that? Like, are we gonna get points taken away if we just do it in our head and write the product?
You will get almost no points if you just write the product.
Okay.
Like out of, let's say this is a 5-point question, I'll give you 2 points if you get the right product. Without any curved arrows. I'm very serious about that. If I ask for the curved arrows, if I ask for the mechanism, you will be getting just more points for the arrows than the product. I reiterate, I do not care if you can get the product without showing me the curved arrows. I need to see that you can derive that. But yeah, that's a good question. I don't mean to get super serious on you specifically, but yes, I need the arrows. I need them to be descriptive of what's happening.
Okay, thank you.
Yes.
What if you were to draw all the curved arrows in one step rather than like drawing the carbocation and then curve arrowing that into the final step?
If you draw the curved arrows like I've drawn in the SN2 down here, and it's supposed to be an SN1, it will be wrong. You will lose all the points for the mechanism. It is the difference. The only reason I care that you know what an SN1 versus an SN2 is because of the carbocation. At that point, everything might as well just be an SN2. That is the difference. I need to see that. Hey, I need to know that you know that that's a neutral nucleophile. It is not a good enough nucleophile to attack an alkyl halide. It's not going to attack until I get a good electrophile in the carbocation, then it's going to attack. There's more to do with carbocations that we haven't talked about yet. But even before that, like it explains why I get different products with an SN1 than an SN2. SN2 gives me inverted stereochemistry, SN1 doesn't. If this was a drug, this wouldn't pass as a drug because it's two different molecules. One of those would work for what you needed to do, the other one wouldn't. So yes, it's all important. Every step of the mechanism. I would not have drawn them out for each one of these things. I know it doesn't ask you that on the active questions and stuff, but that's when you look at my notes. I have spent the time to sit here and draw out every single mechanism because I want you to draw out every single arrow to every single mechanism. I want the answers that are on this practice test should look like the answers that are on your real test. Cool. I don't mean to get too serious about that, but yes, please do not show up on the test and only draw products. You will fail the test. Um, it is, yes. The arrows to me are more important than the product. Fair? Cool. Even if it's not fair, I get to run the class. It's my decision. Cool. So, hopefully this is making sense. Hopefully you guys have more practice. Try to verbalize every single thing that's in every reaction. Try to say, hey, this is the nucleophile, this is electrophile, this is the acid, this is the base, this is an alkyl halide. It's going to be it's the nucleophile's charged. So I get an SN, an SN2. I want try to verbalize, try to describe each reaction in words before you start approaching them. That way you can start to see the patterns. Does that make sense? All right, you guys are killing it. I've got office hours 3 to 5 tomorrow. LAs are going to have a group office hour that was really successful last test. I would suggest you go to it. This is a monster of a test. I'm going to be honest. It's a hard test, and so go to those office hours. I think they're going to be super helpful. You guys are killing it. Yeah, good job. I'm a head off, but feel free to email me with questions you have if you're doing these problems and you get another answer. I can always check an answer. I can always quickly respond and say, hey, you're doing this. Think about this. I'd be happy to do it. So good luck. Let me know if there's anything else you guys need. And yeah.